In the name of Allah. In this lecture, we will talk about a very, very important topic, which is reactive power compensators. When we say reactive power compensators, we mean the various devices and equipment that generate reactive power, as well as the devices and equipment that can consume, absorb, or draw excess reactive power from the electrical network. In other words, reactive power compensators are the devices that can control the increase or decrease of reactive power. Of course, this topic requires at least 10 lectures to cover it in depth, but in this lecture, we will try to provide an overview of the topic as a whole, and we will talk about the traditional devices and equipment used as reactive power compensators, such as synchronous generators or synchronous compensators, series capacitors, shunt capacitors, shunt reactors. After that, we will briefly talk about the modern devices used for reactive power compensation, which fall under the category of flexible AC transmission systems, FACS. At the beginning, we must understand a very, very important piece of information in order to appreciate the importance of the topic we are about to discuss. This is the fact that two of the most important elements of electrical power quality are: the first element of power quality is the improvement or increase of the power factor of the power supply source or of the electrical network as a whole. This will, of course, result in a reduction in the current flowing through the electrical network and consequently a reduction in electrical power losses. The second element of power quality is the control of the reactive power flowing through the electrical network, whether by increasing or decreasing it. This is extremely important for improving voltage levels across the electrical network, and therefore it also leads to a reduction in electrical power losses. We must also understand that the power factor is directly related to the value of the reactive power, and the reactive power is also directly related to the voltage levels in the electrical network. We have previously discussed and mentioned that electrical power consists of three types of power, which are: first, active power, whose unit is watt, kilowatt, or megawatt. This is the power that is actually consumed or used, such as thermal energy in water heaters, mechanical energy in motors, or light energy in lamps and lighting fixtures, and so on. The second type of power is reactive power, whose unit is VAR, kilovar, or megavar. This type of power is not consumed, but rather circulates back and forth between the source and the loads. The third type of power is the apparent or total power, and its unit is volt ampere, kilovolt ampere, or megavolt ampere. And we mentioned that the apparent or total power is the vector sum of both the active power and the reactive power, and of course, we discussed all of this in detail in a previous lecture. The second and most important point is that reactive power is extremely important for the establishment of the magnetic field inside inductive loads or loads that contain windings, such as induction motors or transformers. For this reason, this entire lecture will be dedicated to reactive power, its importance, and its various sources. I also mentioned that power stations are the main source that supplies the electrical network with voltage, frequency, and of course, reactive power. Of course, at the beginning of the development of the electrical network, the electrical loads were relatively close and adjacent to the power stations, and the inductive loads were somewhat limited. I am specifically emphasizing inductive loads because they require large amounts of reactive power, depending on the value of the power factor. Therefore, when these inductive loads were limited in size and located near or adjacent to the power stations, there were almost no issues related to reactive power. However, with the expansion of the electrical network and the tremendous increase in the size of inductive loads, these loads started to require the withdrawal of very large amounts of reactive power. Naturally, the synchronous generators in the power stations would not be able to supply or feed such huge inductive loads with the required reactive power. And we must understand a very, very important point, which is that when inductive loads draw a large reactive current or large reactive power, this will lead to two consequences. The first consequence is a voltage drop at the end of the line. And of course, the more the loads increase, the more the voltage drop will increase. Because, as we know, the voltage drop equals the electric current multiplied by the electrical resistance. Therefore, an increase in the load means an increase in the electric current. We must also understand that the electric current is the vector sum of the active current and the reactive current. We must also understand that when inductive loads draw large amounts of reactive power, this will also lead to a decrease in the power factor of the power supply source. The second issue is the opposite of what we previously mentioned, which is the rise in voltage at the end of the line. This typically occurs when the loads decrease, especially on long transmission lines, and this is due to the Ferranti effect, which is the increase in reactive power at the end of the line, leading to a rise in voltage. Therefore, we must understand that an increase in reactive power beyond a certain value in the electrical network will cause problems such as voltage rise, and similarly, a decrease in reactive power will also cause serious problems such as a drop in the power factor and a drop in voltage as well. That is why it is essential to control the level of reactive power in the electrical network as precisely as possible, without either excess or shortage. We also need to understand the available solutions. What actions should be taken if reactive power increases, and what should be done if it decreases, and how we should handle both situations. That is why the role and importance of the topic of reactive power compensators comes into play. We discussed and understood that the main source of reactive power is the synchronous generators located in the power generation stations. Accordingly, the reactive power will flow through all parts of the electrical network, starting from the power generation station and continuing to the load points or consumption points at the end of the transmission line. Therefore, we can replace the flow of reactive power through all parts of the electrical network and all transmission lines from generation to loads or to the end of the line by installing electrical devices or equipment that act as a source of reactive power, whether connected in parallel or in series with the electrical network components, as we will learn together. As a result, these devices will be able to supply or feed the various loads and different parts of the electrical network with the required reactive power. Consequently, the lines or parts of the network between the source and the load will be dedicated solely to or will only carry active power. Naturally, this means a reduction in the total power or the total current flowing through the network. This in turn will help improve the issue of voltage drop and reduce electrical losses, because through this measure, the only requirement from the source is to supply the loads with active power only. Accordingly, we understand that the devices used for reactive power compensators, whether they are installed in series or in parallel with the components of the electrical network, whether traditional equipment or modern electronic devices known as FACTS, flexible AC transmission systems, have the following main functions. First, primarily controlling the value of reactive power and thus enabling control over the voltage level. Second, also controlling the active power. Third, controlling the value of reactance, whether inductive reactance or capacitive reactance, and therefore, of course, controlling the overall impedance of the network. In addition, they provide control over the phase angle between different stations. We will begin together with the traditional devices or equipment used as reactive power compensators. These traditional devices and equipment serve as sources of reactive power or enable us to control the flow or transmission of reactive power through the electrical network. The most important traditional equipment used as reactive power compensators are synchronous compensators or synchronous generators, series capacitors, shunt capacitors, shunt reactors. The first device among the traditional sources of reactive power is the synchronous compensator, and the first type of it is the electrical generators or synchronous generators located in the power generation stations. As previously mentioned, synchronous generators are the main source that supplies the electrical network with voltage, frequency, and reactive power. However, it is important to understand that the amount of reactive power supplied by synchronous generators to the electrical network or to the inductive loads is limited and insufficient. The second point to consider is that generating a large amount of reactive power from synchronous generators will naturally come at the expense of generating active power from the same generators. In other words, the more reactive power is required to be produced, the less active power can be generated by the same synchronous generator. The second type of synchronous compensators is the synchronous motors. It is important to understand that these synchronous motors are unloaded, meaning they operate without any mechanical load. Secondly, synchronous motors are structurally identical to synchronous generators. However, the main difference between them is that synchronous motors are unloaded, meaning they have no loads connected to them and therefore do not consume any active power at all. This is in contrast to synchronous generators, which are connected to loads and thus supply both active power and reactive power. Another important point is that synchronous motors produce only reactive power, which means we can obtain reactive power from synchronous motors at levels greater than those that can be provided by synchronous generators. Next, we will talk about the capacitors that are connected in series with the transmission line, or series capacitors in general. Of course, we all know that capacitors in general have capacitive reactance, and a transmission line naturally has inductive reactance. Therefore, installing capacitors in series along the length of the transmission line will naturally reduce or help eliminate part of the inductive reactance of the transmission line. This, of course, means that we are reducing the impedance of the transmission line. And as long as we reduce the impedance of the transmission line, it means that we can increase the length of the transmission line for the same amount of electrical power to be transmitted. The second point is that we all know the flow of electric current through the transmission line in the presence of the line's impedance will naturally result in a voltage drop. This means that with increased loading and increased current flow, we will observe that the voltage at the end of the transmission line will reach an unacceptable or low value that is not suitable for the loads. Therefore, installing capacitors in series with the transmission line will lead to an increase in the voltage level. And of course, we all know that the higher the voltage, the more electrical power we can transmit through the same transmission line. The second point is that the reactive power generated by the series capacitors will increase with increased loading. This naturally results in improved voltage regulation. The third and important point, as we all know, is that capacitors are a source of reactive power. However, when capacitors are connected in series with the transmission line, they primarily work to improve or increase the voltage level first, and then subsequently improve or raise the power factor. But it is important to understand that the primary purpose of connecting capacitors in series is to increase the voltage. The improvement in power factor is a secondary effect. This is in contrast to capacitors connected in parallel, where the main objective is to improve and raise the value of the power factor, and then as a result, the voltage is improved afterward. As I mentioned earlier, connecting capacitors in series with the transmission line will lead to an increase in the voltage level. But does this mean that the capacitors should remain connected continuously? Of course not, because if these capacitors remain connected continuously, especially during periods of light loading, they will cause a significant and undesirable voltage rise, which is technically unacceptable. Therefore, it is necessary to install shunt reactors alongside them. However, we must understand that the continuous connection and operation of shunt reactors will reduce the capacity of the transmission line to deliver the required electrical power. For this reason, one of the main disadvantages of these series capacitors is that they tend to remain connected continuously. Let us now talk about shunt capacitors, or the capacitors that are connected in parallel. As I mentioned earlier, the primary purpose of connecting capacitors in parallel with the electrical network or with various electrical loads is to improve or increase the value of the power factor of the power supply source. This means that the power supply source or the generating stations will supply the electrical loads mainly with active power, along with only a small portion of the reactive power. The larger portion of the reactive power required by the electrical loads will be supplied through these capacitors. And of course, this means that the electrical power or the electric current flowing through the transmission lines will decrease. Naturally, this also means that the voltage drop will be reduced and the power losses will also decrease. As a result, the voltage value at the end of the transmission line will improve due to the reduction in voltage drop. Therefore, we understand from this that the primary function of capacitors connected in parallel is to improve or increase the value of the power factor, and this is then followed by an improvement in voltage or an increase in the voltage value. However, it is important to understand that one of the most significant issues with shunt capacitors is that the reactive power they produce is directly proportional to the square of the voltage. This means that if the voltage decreases, the reactive power output from these capacitors will also decrease accordingly. Let us now talk about shunt reactors. To begin with, it is important to understand that the primary function of shunt reactors is to absorb reactive power, or more precisely, to absorb or draw capacitive reactive power at the end of long transmission lines. As we all know, there is the Ferranti effect, which is the phenomenon where, due to the long lengths of transmission lines, whether cables or overhead transmission lines, and especially during light loading conditions, there is a noticeable rise in voltage at the receiving end of the transmission line. This voltage rise can certainly cause damage or failure of electrical equipment and insulators at the end of the transmission line. That is why shunt reactors must be installed at the receiving end of long transmission lines. The function of these shunt reactors is to absorb or draw the excess reactive power, thereby reducing the voltage level at the receiving end of the line. However, we must also recognize some of the disadvantages of installing shunt reactors. One of the major issues is that we are dealing with a very large amount of capacitive reactive power, which means that the circuit breakers capable of handling this capacitive reactive power will be extremely expensive, especially considering we are operating at high or extra high voltage levels. Another important point is that shunt reactors are usually operated manually, and this leads to another major problem. If there is a sudden disconnection of any large load, this would result in a sudden increase in reactive power, and if the shunt reactor is disconnected or out of service at that moment, then a voltage rise will occur at the end of the transmission line, as we mentioned earlier, which can lead to damage or failure of electrical equipment. The main issue here is that it is technically unacceptable to keep the shunt reactors permanently and continuously connected under all operating conditions. This means that there is a need to repeatedly connect or disconnect the shunt reactors depending on the variations in load. This, in turn, leads to a very, very, very slow response. And all of this represents one of the most significant disadvantages of traditional devices. This is in contrast to modern devices, namely flexible AC transmission systems, FACS, which are characterized by fast and automatic response to any changes in load or voltage. And the last point is that one of the major disadvantages of shunt reactors is that the absorption of reactive power leads to an increase in wasted energy or power losses. The second point is that the continuous connection of shunt reactors, especially during high load conditions, will result in a reduction in the capacity and capability of transmission lines to carry or transmit the required electrical power. Therefore, it is necessary to disconnect these shunt reactors during periods of high load. We will then talk about the modern technologies or devices for reactive power compensators, which are part of the flexible alternating current transmission system, or FACS. And of course, these modern devices are high-power electronic equipment such as the Thyristor. Some of them are installed in parallel with the electrical network components, while others are installed in series with the electrical network components and transmission lines. All of them, of course, act as either sources or consumers of reactive power. The most important advantage they have over the traditional types that we previously discussed is that they are controlled using modern control methods with a very fast response. Naturally, their functions also include the control of reactive power, voltage control, active power control, control of reactance values, and also control of the phase angle between substations. The first advantage of flexible AC transmission system, FACS devices, over the traditional equipment we previously discussed is that FACS devices contain both capacitors and inductors at the same time. This, of course, means that these devices can generate inductive reactive power or capacitive reactive power. Naturally, this means that these devices can generate, consume, or absorb reactive power. This implies a rapid response or quick reaction to any change in the value of the network voltage, whether it increases or decreases. This fast response or quick decision making is due to the fact that the control of the amount of reactive power is achieved through thyristors and electronic circuits, which is significantly faster or incomparable to the traditional equipment we spoke about a few minutes ago. The most important devices of the flexible AC transmission system, FACS, are 1. Static VAR Compensator, SVC. 2. Static Synchronous Compensator, STATCOM. 3. Static Synchronous Series Compensator, SSSC. 4. Unified Power Flow Controller, UPFC. The first device from the flexible AC transmission system, FACS, is the Static VAR Compensator, SVC. It is the simplest type of flexible AC transmission system FACS devices, and it consists of inductors and capacitors connected in parallel with each other. Therefore, we understand that the difference between the Static VAR Compensator SVC and traditional devices is that in traditional equipment, either capacitors or inductors are used, but here we find both inductors and capacitors present at the same time. As a result, we can connect or disconnect either the capacitor or the inductor, and at any desired ratio, all through thyristors controlled by electronic control circuits. The Static VAR Compensator SVC is installed when there are large variations in voltage values over short periods of time or during brief intervals. Therefore, by using Static VAR Compensator SVC devices, we can maintain the voltage levels of the electrical network within safe and acceptable limits. It is important to know that there are 3 types of Static VAR Compensator SVC devices, which are 1. Thyristor controlled reactors, TCR. 2. Thyristor switched capacitors, TSC. 3. A combination of TCR and TSC. It is also important to understand that Static VAR Compensator, SVC, devices, or flexible AC transmission system, FACS devices in general, are not connected directly to high voltages because they operate at limited voltage levels. That is why we usually observe the presence of a step-down transformer between the high-voltage transmission lines, or the electrical network in general, and the Static VAR Compensator SVC devices. However, the traditional devices we discussed a few minutes ago, such as Shunt Reactors, are directly connected to high-voltage levels. Thus, through the Thyristor-controlled reactor, TCR, and as long as we mention the term reactor, we understand that the function of the Thyristor-controlled reactor system is to facilitate the easy absorption or withdrawal of any excess or unwanted reactive power. However, with regard to the Thyristor switched capacitor, TSC system, and as long as we mention the term capacitor, we understand from this that the function of the Thyristor switched capacitor system is to generate or produce the required reactive power. The third system is the TCR-TSC, which of course means a combination of the 2 previous systems. Accordingly, it becomes very easy to either generate or absorb and withdraw any amount of reactive power. Among the most important advantages of Static VAR Compensator devices are 1. Ease and speed of controlling reactive power. 2. The ability to easily generate or absorb any amount of reactive power at any time, which of course means stabilization of the network voltages, especially the voltages at the ends of long transmission lines, particularly during light load conditions. 3. Static VAR compensator systems also contribute to reducing electrical power losses in the network and increasing the capacity and capability of the electrical network to transmit higher or greater amounts of electrical power. However, the disadvantages of Static VAR compensator devices include: first, high cost. Second, the size of the reactors and capacitors is somewhat limited, and therefore the amount of reactive power that can be generated or absorbed will also be limited. Third, the capacitive reactive power is affected by voltage reduction. This, of course, means that the generation of capacitive reactive power will decrease with the drop in the electrical network voltages, since reactive power is directly proportional to the square of the voltage value. Here is an example of Static VAR compensator devices. Another image of Static VAR compensator devices. The second device among the FACS devices is the Static Synchronous Compensator, STATCOM. The Static Synchronous Compensator, STATCOM, is considered an advanced development of the Static VAR compensator, and naturally this means it is also connected in parallel with the network. The second point is that the Static Synchronous Compensator, STATCOM, consists of inverters, and instead of using the conventional Thyristor, it utilizes a more advanced type of Thyristor known as the gate turnoff, GTO. One of the most important advantages of the gate turnoff, GTO, Thyristor, is that the switching operations, turning on and off, are much easier and faster compared to the conventional Thyristor. Another key advantage of the static synchronous compensator, STATCOM, is that it does not use capacitors or reactors, yet it is still capable of generating or absorbing large amounts of inductive reactive power or capacitive reactive power. Among the most important features of the static synchronous compensator, STATCOM, is its small size or compact physical footprint. This is, of course, due to the fact that it does not require capacitors or reactors which typically need large space, as is the case with the static VAR compensator. Another major advantage of the static synchronous compensator, STATCOM, which distinguishes it from the static VAR compensator, is that its ability to generate capacitive reactive power is not affected at all by the network voltage. In the image before us, there is an example of a static synchronous compensator, STATCOM, installed inside a substation. The third device among the flexible AC transmission system FACS devices is the static synchronous series compensator, SSSC. The static synchronous series compensator, SSSC, is very similar to the static synchronous compensator, STATCOM. However, this device is installed in series with the network, unlike the static synchronous compensator, STATCOM, which is connected in parallel with the network. And since this device is connected in series with the network, it enables us to change the value of the reactance, X, of the transmission line. This means, of course, that we can increase or decrease the amount of electrical power transmitted through the transmission line, all without making any physical modifications to the transmission lines. Another key advantage of the static synchronous series compensator, SSSC, over conventional series capacitors, capacitors connected in series, is that the static synchronous series compensator, SSSC, is not affected by the value of the electric current flowing through the transmission line, unlike the series capacitors, which are directly influenced by it. The second point, as I mentioned before, is that static synchronous series compensator, SSSC devices, are connected in series with the transmission lines. Therefore, and quite simply, they can act as an inductive reactance, and thus they can work to impede the flow of electrical power. Consequently, they are capable of reversing the direction of electrical power transfer, and this, of course, is achieved through changing the phase angle. The fourth device, or the last device among the flexible AC transmission system, FACS devices, is the Unified Power Flow Controller, UPFC. The Unified Power Flow Controller, UPFC, is composed of a static synchronous compensator, STATCOM, and a static synchronous series compensator, SSSC. And of course, we all know that the STATCOM is connected in parallel with the network, while the SSC is connected in series with the network. Therefore, we understand from this that the Unified Power Flow Controller, UPFC, is connected both in series and in parallel with the network. Naturally, this means that this device incorporates the advantages of both of these devices. The last thing we need to know is that Unified Power Flow Controller, UPFC devices consist of electronic circuits made up of a group of gate turnoff, GTO, thyristors, as well as a control unit whose function, of course, is to control the amount of active power that is required to flow through the transmission lines. It also controls the value of reactive power, the voltage levels of the transmission lines, and the phase angles of the voltages at the sending and receiving ends of the transmission lines. In addition, it controls the value of the reactance, X, or the impedance, Z, of the transmission network lines. In front of us is an image, example, or diagram of a Unified Power Flow Controller, UPFC, with a voltage of 500 kilovolts. The last point in today's lecture is about static switches, and it is important to know that FACS devices are connected and disconnected through Thyristor switches or static switches. Therefore, we need to understand together what the main advantages of static switches are compared to the traditional circuit breakers that we know, such as the SF6 circuit breaker. Among the advantages of static switches, first, the fast response in switching, connection and disconnection. Second, we can precisely control and select the exact switching moment with respect to the alternating voltage waveform, meaning we can choose to switch during the positive half cycle or the negative half cycle, which results in extremely accurate switching. Of course, these are electronic switches, so there is no electrical arcing during switching. Also, they require no periodic maintenance, which results in a long operational lifespan. In addition, there are no moving parts, so they are unaffected by vibrations and produce no noise or sound. However, the main disadvantage of these switches is the high electrical power losses compared to traditional or conventional circuit breakers that we are familiar with. Thank you for your attention. See you in the next lecture.